96.65%. Okay, just picture this. Trying to map every single physical change that's happened to a vast semi-arid landscape over 4 entire decades. Doing that manually with old-school surveys, it would literally take a lifetime. And let's be honest, it would probably be absolutely riddled with human error. But recent studies are showing that by utilizing deep neural networks in platforms like Google Earth Engine, artificial intelligence can now map decades of land use and land cover changes with up to 96.65% accuracy. It's just a staggering figure, right? And it instantly shows us the profound, absolute game-changing capabilities of modern environmental tech.
So welcome to The Explainer. Today, we're taking a massive deep dive into a paradigm shift that is completely fundamentally revolutionizing environmental impact assessments. We are finally ditching those dusty binders of static paperwork, and we're leaping headfirst into the era of artificial intelligence and real-time geographic information systems, or GIS. We're going to explore how we're shifting from this old-school, static, retrospective reporting to building living, breathing digital models of our actual ecosystems. And what that means for us is faster development, way better protected habitats, and ultimately smarter cities for everyone.
Here is our roadmap for today. First, flaws in static environmental reviews. Second, the AI and GIS revolution. Third, real-time environmental monitoring. Fourth, building environmental digital twins. And finally, a sustainable AI future. Let's get right into it.
Section 1. Flaws in static environmental reviews, or, as I like to think of it, the problem with paperwork.
To really appreciate this new solution, we have to understand the fundamental baseline problem with how traditional ecological assessments have been handled for decades. Traditionally, environmental impact assessments, or EIAs, have been purely descriptive and qualitative. They rely heavily on manual field surveys that, frankly, take months or even years to compile. By the time that massive, heavy report is finally published and a construction project actually begins, the ecological baseline is completely stale. The data is already out of date before day one. On top of that, things like cumulative effects, how different environmental burdens actually stack up over time, they're usually just treated narratively in a brief little paragraph. The urgent, definitive solution here is shifting to real-time tracking, predictive forecasting, and AI-driven living models. It compresses that huge lag between observing a problem, testing a scenario, and actually designing a strategy to fix it.
Section 2. The AI and GIS revolution. The brain and the map. Think of this as mashing up the ultimate brain with the ultimate map. For the longest time, geographic information systems, or GIS, were mostly just used as digital display boards to generate static maps. But AI is finally turning them into predictive, highly analytical engines. When a new transport corridor or, say, a housing development is proposed across a physical landscape, we need to know exactly how it's going to fragment that specific habitat. By seamlessly integrating AI remote sensing into a GIS workflow, we aren't just looking at a single frozen snapshot in time anymore. AI algorithms can literally ingest decades of satellite imagery and automatically highlight the entire history of disturbance and change over that exact terrain. It provides this incredibly deep spatial evidence layer that is both repeatable and highly accurate.
And this integration, it shifts everything. We move completely away from those isolated, hyperlocal ecological reviews that tend to miss the forest for the trees, and we step into a fully integrated, landscape-level assessment. The absolutely crucial takeaway here is that integrating ecological models with GIS tools allows city planners to see the real ripple effects of a project across aesthetic, ecological, and cultural values, but over a much, much larger regional scale.
To give you a super concrete example of this AI-GIS integration in action, just look at what the U.S. National Oceanic and Atmospheric Administration, or NOAA, is doing right now. They're using AI to triage incredibly high-resolution satellite imagery to monitor the endangered North Atlantic right whale. Basically, the AI acts as a massive filter. It scans millions and millions of pixels to flag potential whale locations on the map. This means human experts don't have to endlessly stare at images of empty ocean. They can focus purely on verifying the flags the AI caught. The benefit is just immense scale and speed without removing that absolutely necessary expert human judgment.
Section 3. Real-time environmental monitoring. The sensory network.
So, we've got the GIS map and we've got the AI brain. But how on earth does that brain actually know what's happening out there on the ground right now? Well, it happens through a massive hardware revolution called AIoT, or the artificial intelligence of things. Now, you've likely heard of the Internet of Things, just hooking sensors up to the internet, right? But AIoT takes it a massive step further. by embedding lightweight machine learning models directly onto those edge devices out in the field. This means a sensor sitting in a remote forest doesn't just blindly send raw data over a super weak cellular network. Instead, it processes the data locally, filters out all the background noise, and detects anomalies right there on the edge. This completely democratizes territorial monitoring. It makes the network incredibly resilient, even in rural areas where connectivity is spotty at best.
So what exactly are these AIoT sensors tracking out there? Honestly, almost everything. They're monitoring particulate matter in the air, atmospheric CO2, ambient noise levels, the sudden presence of toxic algae in surface water, and even forever chemicals like PFAS in groundwater. There's a fascinating case study of this down at the Hub Ambiental del Caribe in Colombia. They didn't even bother building entirely new infrastructure from scratch. Instead, they brilliantly converted their existing public lighting networks into a 90-node miscomputing sensory grid. So their streetlights are now actively measuring local air quality and noise, creating this amazing high-frequency intelligence network for the entire community.
To really wrap your head around the staggering scale of these sensory networks, consider this number: 100,000. A 2025 study in Nature Ecology and Evolution detailed a biodiversity monitoring system built around always-on bioacoustic sensors spread across 580 permanent locations. Because these sensors are constantly listening, 24/7, and using AI to identify bird calls, they captured over 100,000 bird detections. That is a scale of continuous, reliable data collection that a team of manual human field surveyors simply could never achieve. And through that, they were able to identify 263 different species.
Which brings us to Section 4, Building Environmental Digital Twins, from static to live. We've talked about the AI brain, the GIS map, and this incredible AIoT sensory network. What happens when you combine the whole shebang? You get the Autonomous Digital Process Twin, or ADPT. We finally crossed the bridge from static paperwork to a live environment. It is super vital to understand that a digital twin is not just a fancy 3D digital replica or a neat dashboard. It's a living, dynamic virtual representation of a physical socio-ecological system. It utilizes continuous real-time data feeds from our AIoT sensors, and it uses reinforcement learning to actively simulate the environment. This means planners can safely test wildly complex ecological scenarios, like, say, exactly how a new dam is going to affect downstream habitats in the virtual world before ever touching a shovel in the real world.
The real magic here is how these layers form a continuous loop. Step 1 is the data acquisition layer. Those distributed AIoT sensors gathering real-time facts from the mud and the air. Step 2 is the virtual modeling layer, where all that data synchronizes with our GIS map and our dynamic simulation models. Step 3 is the intelligence and analytics layer. This is where AI decision models test different scenarios and optimize for the best possible outcomes. And finally, Step 4 is the governance and execution layer, where real institutions actually take action based on these insights. And because it's a loop, those sensors immediately measure the real-world impact of that institutional action, and the cycle starts all over again. It's a continuous, recursive, cybernetic loop.
Now you might be sitting there wondering, okay, sounds cool, but does this highly technical model actually yield real-world results? Oh, absolutely. Research published in 2022 showed that applying digital twin technology to optimize real-time operations and maintenance can reduce greenhouse gas emissions and energy costs by approximately 21%. This isn't just theoretical modeling up in the clouds. It is tangible, proven ROI that drives down both emissions and consumption at the exact same time by predicting exactly where efficiencies can be made.
Section 5. A Sustainable AI Future. The Human in the Loop.
With all this automation, edge computing, and digital twin simulation doing the heavy lifting, you might wonder, where do the humans go? Well, the answer is right into the loop. These advanced systems are explicitly designed to direct human expertise where it matters most, never to replace it entirely. Digital twins inherently empower human governance, specifically when it comes to regulatory compliance. For instance, mapping location-specific impacts directly supports the updated GRI 101 Biodiversity Standard. Monitoring socio-ecological risks in real time, that aligns perfectly with the new GRI 14 standard for the mining sector. By having a living digital twin, human auditors and sustainability officers can remarkably and efficiently map location-specific, real-time impacts directly to these rigorous global reporting frameworks.
There's a quote from Yenmer Research in 2026 that just hits the nail on the head regarding the philosophy behind all of this. AI only helps trust in environmental review when its outputs are inspectable. Transparent decision support is about making assumptions easier to examine, not hiding them behind automation. And that's exactly it. The true power of this technology lies in transparent, inspectable AI. By using large language models to translate those complex algorithmic outputs into plain, everyday language, we ensure that these tools empower vulnerable communities, they foster genuine climate justice, and they keep decision makers accountable.
So we've seen how mashing up AI, GIS, and real-time sensor networks is changing the game, allowing us to map decades of history, predict future outcomes, and simulate real-world impacts long before they ever happen. We are finally, thankfully, evolving from static, dusty paperwork to living digital twins. So I'll leave you with this provocative thought. If our ecosystems are living, breathing networks, shouldn't our environmental protections be too? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.